In the last part of the slides, I introduced that we can have structured grids. Structured grids, for example, are Cartesian grids like checkerboards. But you can use this if you don't have a complicated geometry or you're not so interested in really geometry details. You just take this checkerboard Cartesian mesh. But if you need more details of the geometry, if you need more details of your flow field, of your temperature field, or of your magnetic field, you choose another grid type. Then you will maybe decide to take an unstructured grid. What is the difference here? If you have an unstructured grid, not every cell, it is not logical which neighbor every cell has. This cell can be, neighbor can be here, the neighbor can be here, or here, or here, or here, or you can even come back to the cell where you started. Yeah? It's not necessarily that if you go into one y or k direction with your indices that you come to your right position at x or at y. This means you have an unstructured mesh. Unstructured meshes can be two-dimensional, three-dimensional, and there are many different base cell types that can build up this unstructured mesh. For example, we can have triangles, we can have prisms, we can have quads to build up such cells that are more or less triangles or pyramids, or quads are typical cells. But you can have more cells in three-dimensional, you can have tetrahedral cells, you can have pyramids, you can have polyhedrons with a lot of different edges and vertices here. You can have prism and base wedges, or you can in three-dimensional have your hexahedral, your easy quad mesh cell type. And if you have the quads and you build your whole mesh with quads, you will have a structured mesh. And if you build your whole mesh with pyramids, you will get an unstructured mesh. Okay, then let's have a look at the syntax, at the wording, because if we in the lectures, if we want to talk about cells, you have to know what is what, and maybe refer also to the slide to read it a bit better. First we speak cell of control volume. I've already introduced this syntax. And we speak of nodes. Nodes or grid points are always the edges. The nodes are here always at the edge of the cell. We speak of cell centers. Cell centers are always in the middle of the cell, and that's why do we need the cell center. That's not a real coordinate. Normally we have the coordinates are always the nodes. And why do we need the cell center? In this position is mainly the phi value stored. The momentum or the velocity or the mass or the pressure is in many cases stored in the cell center. And to calculate the cell center, we need vector mathematics. And we speak of edges. The edges are at the side of the cell, of the box. And we speak of faces, the faces of the cells. Okay, and we speak of domains. Domains are whole meshes. We can have simulations with separate domains. We can make one cylinder and the next cylinder of an engine and couple it together. the fluid can flow from one cylinder to the next cylinder. Okay, then let's have a look at the structured grids. If you, for example, we often have this elbow. I will show you much more about this elbow problem. Here comes fluid inside and comes fluid from the other side. Also showed you this behavior at the introduction slides, the famous case. And now how can we build this geometry before we make such a structured mesh, the coordinate system that looks like this elbow? We have to think a bit, how can we do it? Yeah, for example, we can make such a computational grid like this, and then we make a small mesh here, and we have also coordinates here, they exist, but we have to tell the program they are dead cells, dead regions, we don't need them, we cut them away here to make the calculation. Okay, there are another simple blocks. If you want to make, for example, this can be a pipe where water can flow inside from here to here, and if you want to build up these easy pipes with hexahedral meshes, we will make a block here, a mesh here, and we have to couple it with a block here, a block here, and here, and here. And what is important, if you have structured meshes, it is important that every cell face here had a neighbor cell face at the other side. We can't have 5 cells here and 100 cells here. This will be mathematically undefined. Okay, that's another, and it's a more simple workflow here. It gets more complicated if we have round geometries. It's possible, but to fill a quad block or a rectangular block into a round geometry, a bit more advanced. Now you will see this later. This is a quite good solution here. We have a quad block. We added here also quad blocks, and we just banded the edges a bit. Okay, and also in this problem it's important to prevent 90-degree angles. Okay, it's also same problem. This mesh is not so good. Here's also a round geometry. We have a block in the middle, blocks at the sides, and here we see it's not so good work. We have really bad quality of the cells here and bad quality of the cells here. Okay. Yeah, that's multiblock geometry. Multiblock geometries, then we solved the solution. We made a block here, a block here, a block here. Every block has a rectangular checkerboard-like mesh, and every cell has a defined neighbor cell. So we will we can model a round geometry with a hexahedral cell structure. Okay, so let's have a look at unstructured meshes. We had a look at structured meshes. Let's look a bit more at unstructured meshes. What happens if we have our Dino here, our T-Rex? You cannot make checkerboard mesh to model this complicated T-Rex geometry. You need more complicated cell structures, and in many cases you can also use multiblock meshes. So here is a cell face of an unstructured mesh. You see it looks a bit like a structured mesh here, but at this region you see it's unstructured. Or here it looks like, from here, if you come from here, looks like a structured mesh, But here you see it's an unstructured region. You have to look a bit close. Yeah? Not every cell has a neighbor here. Or let's come to more advanced meshes. Yeah? Maybe you can imagine what this geometry looks like. Looks a bit like a car. Yeah? We made a geometry with a bumper, and here's a window, and it's a round car geometry. And to make it a mesh for this car geometry, you can imagine it's difficult to use hexahedral meshes. It's more easy to use tetra meshes. And there's one thing I want to mention. If we come nearer to the bumper, or nearer to the front, nearer to the metal, yeah, to the surface of the car, we have to make here finer mesh structure to get the boundary flow over the car, get a better quality. Or if you have a look at this, it looks like a bit like a piston. I think it was an exhaust gas treatment duct. And if you take a look here, this region is important for fluid flow. We have to model it in good detail. We use tetrahedral meshes here, tetraheders, but here at the bottom it's too time consuming for the computer to solve tetraheders everywhere. Here we use this easier hexahedral structure, and we put it together, both mesh types, we coupled it, and we got a hybrid mesh structure. Yeah, that's also, I hope you can see what it means, what it is. It's a car, it's a body of a car, here's a wheel, bumper, here's the engine, and that's always something that is interesting for the engineers. How can you get enough air into the room where the engine is? How can we get the air inside, and how can we cool the engine down? How can we optimize the fluid flow around this engine here to get a cold engine? And it has to be modeled, and of course this will be really tough work for hexahedral cells, so we probably will use tetraheders geometries for this case. Or this, also hybrid mesh. Here we have this chamber, and here this chamber gets a bit thinner. That's not a problem. You can define the geometry also for hexahedral meshes, but here from this position you can maybe see it. I hope you can see it. Please look at the slides. Here the mesh structure changes, and you get prism cells. Okay.